Good morning to you. In this particular video, we are going to discuss carbocations. And in this video and onwards, we are going to complete all the reactive intermediates called carbanion, benzene, nitrene, arine, free radical, each and everything. And in particular carbocation, we are going to cover all the aspects: its structure, its stability, the rearrangement reactions associated with it, the ring expansion and ring contractions possible in the carbocation while carbocation is forming, addition reactions associated with carbocation, all the addition reactions I have listed where carbocation is getting formed, that is H plus water addition, HX addition, X2 means halogen. Halogens means generally chlorine and bromine. Fluorine reactions is not so good and iodine reactions is reversible. Next, NBS, N-bromosuccinamide or N-iodosuccinamide, this addition. Next, BH3 and H2O2 NaOH, this reaction is hydroboration oxidation. Here also carbocation is formed. Next, HgOAc(2), mercuric acetate, and second step water NaBH4. This reaction is oxymercuration demercuration. So all these addition reactions are associated with carbocation. We are going to discuss all of them, and I will ensure you all your queries about all these reactions and possible rearrangements will be clarified after this video. Next, two very important name reactions are associated with carbocation. One is pinacol-pinaclone rearrangement. We are going to discuss it in multi-dimensional way. Its stereochemistry, its rigid system, its shear form, etc. So many things are there to discuss in pinacol-pinaclone rearrangement. Then one is dinone-phenol rearrangement. Okay, this is simple one. So all these aspects we are going to cover in this video and the upcoming videos. Okay, so let's get started with carbocation and its structure. Carbocation is a reactive intermediate. So before knowing carbocation, let's discuss about intermediates or reactive intermediates. So intermediates. What are intermediates? In very simple way, we know in chemistry, in a particular reaction, reactant is getting converted to product. Sometimes it is a multi-step reaction, number of steps equal to 1. Sometimes number of steps are more than 1. So this is multi-step reaction. In multi-step reaction, apart from reactant and product, many things form within the reaction. Suppose reactant and product, but to convert from reactant to product, 3 different species A to B to C is forming, finally C is giving the product. So A, B, C are neither reactant nor product. So these are intermediates. Suppose A is a neutral molecule. Okay, A is neutral, or stability is very, very high, or stability very, very high means it stays in the reaction mixture for a very long time. Then we can say its lifetime is very high. And in every cases we can isolate them. Okay, in every case we can isolate them. So A is intermediate, but A is not reactive intermediate. Suppose B is very reactive. Its lifetime is very low. Its stability is very less compared to neutral molecules. Okay, and this is mostly not neutral, but there are neutral reactive intermediates also. So mainly its lifetime is very less and it is very reactive. Then B will be called as a reactive intermediate. But A is intermediate, but A is not reactive. Okay, suppose C is similar to A. So here A and B are reactive intermediates. A and B is intermediates only. Sorry. A and C is intermediate. B is intermediate, and more specifically it is reactive intermediates. So these are very difficult to isolate. Then we are going to, as these are very difficult to isolate because its lifetime is very less. Suppose lifetime is 10 to the power minus 7 second. That means in 10 to the power minus 7 second, it will convert it into other products. So it's very difficult to trap it. So this is our major discussions on these species. Those are very reactive and intermediates. So these are reactive intermediates. There are few reactive intermediates known till now. These are carbocation, carbanion, free radical, carbene, nitrene, benzene. This is a type of arine. A-R-Y-E-N. Arine. There are more type of arine. Benzene is a type of arine. So name of reactive intermediates is arine. So we are going to discuss all of them and with that much of details. All name. First we will discuss about structure. Then we will be discussing about, as I have shown you before, stability, rearrangement, and all possible reactions associated with them. Okay, in this upcoming video. So let's discuss about carbocation structure. Structure of carbocation. You can make point. Structure of carbocation. So let's discuss all aspects of carbocation in a more specific way. Let's draw a carbocation. Carbocation is sp2 hybridized. Carbocation is, first point you can write sp2 hybridized. That means carbocation is planar. sp2 means planar, and more specifically trigonal planar, right? sp2 corresponding geometry or shape is trigonal planar. Next, as it is sp2, the bond angle will be 120 degree. As it is sp2, as it is planar, let's draw its structure. Suppose this is carbon and one group is above the plane, some group is below the plane. All this it is in a plane, in a horizontal plane actually, the plane perpendicular to the board. Suppose group here is A, B, C. Let's understand the hybridization a little bit. sp2 hybridization. Carbon has one s subshell in valence shell and 3p subshell. Okay. Suppose these are px, py, pz. One s and two p will combine to form sp2 hybrid orbital. sp2 equal energetic or degenerate sp2 hybrid orbital, and one pz orbital will be vacant. So in this particular structure, if we join A, B and C, we will be getting a trigonal planar geometry. Sorry. Sorry. Okay. A previous file has been came. Okay. I am discussing with this file. Okay. So yes. So this is our trigonal planar structure. sp2 hybridization. 2s, 2px, 2py, 2pz, and this combines to sp2 hybrid orbital, and one pz orbital is vacant. And here I have drawn that particular pz subshell, pz orbital, right? So this is vacant. So first point is sp2, as this has 3 sigma bond, okay, carbon A, carbon B, carbon C. So 3 sigma bond, and each sigma bond contains 2 electrons. So it is of 6 electron species, so electron deficient species. Then bond angle 120 degrees, geometry is trigonal planar. So all of this, these are all about carbocation. Okay. Now we are talking about, we are going to talk about stability of carbocation. I am erasing this and starting again. Okay. There is a network glitch or something. There are few effects. Before knowing the stability, I am assuming that you know all of these things. mesomeric effect, resonance effect, hyperconjugation, inductive effect, aromaticity. All these are part of GOC, general organic chemistry. I expect that you are aware of this. Among all these effects, there are few effects that stabilizes a carbocation. Suppose carbon, there is a group methyl, CH, H, H, this is methyl group, and suppose another two is H. This is carbocationic carbon. This carbon is alpha carbon, the nearby, the associated, the vicinity, the carbon close vicinity with that carbocation, this is alpha carbon, and these three are alpha hydrogen. This alpha hydrogen can donate its lone pair of electron, and it can form like hyperconjugative structure. You all know that. So this is plus H effect. Plus H effect stabilizes the carbocation. Okay. Similarly, resonance. Suppose this is carbocation and this is one group. This can undergo resonance. This carbocation can undergo resonance, and the resulting structure will be like this. Okay. So plus R, plus resonating, plus resonance, this can also stabilize carbocation. Next, mesomeric. Suppose carbon positive and suppose OMe, O-methyl. Oxygen lone pair can donate here, C double bond O-Me. Suppose two different groups are there. Yes. So this will be resonating structure. This will be called mesomeric effect. When there is a lone pair, suppose oxygen, nitrogen, sulfur, etc. So lone pair containing species, when give electron to the adjacent carbocation, adjacent carbon with positive charge, then this is called mesomeric effect. And inductive effect, you can say that suppose this is methyl group, it is pushing electron with sigma bond. This is inductive effect. This is plus I effect. So plus M, plus R, plus H, plus I, all these effect stabilizes the carbocation. Another one is aromaticity. In aromaticity point of view, we can say that when a particular species is aromatic due to positive charge on carbon, so this will be stable due to aromaticity. Suppose this particular carbocation, this is anti-aromatic, so aromaticity is not there, and it is anti-aromatic, this is not stable. Suppose this particular carbocation, this is tropylium cation, this will be aromatic, 6 pi electron, this is cyclic, this is planar, this is full conjugation, and 6 pi electron. So according to Huckel's rule, this will be aromatic, so this is very much stable. So aromaticity is one point, and the order of this, when in a particular comparison all of these things are coming, then we have to arrange them. Okay, the arrangement will be done on first something will be preferable called dancing resonance, then aromaticity, then resonance, then hyperconjugation, then inductive effect. This will be the order, but there are slight competitions in it. Sometimes more aromaticity or more resonance or more hyperconjugation may dominate over few resonance. We are going to discuss all of them with different examples in the upcoming videos. Okay, so in next video we will be discussing relative comparison with all type of examples, and all your queries will be clarified. So these are the stability criteria. So after this video I will be suggesting you to clear all of these concepts or read or revise all of these concepts of basic organic chemistry, so that you understand the topic of next video, that is relative comparison of stability of carbocations. Okay, if you are okay with all of this and you think you all are okay and no need to revise, then you can come to the next video, which will be about comparison of stability of carbocation, and after that we will be covering one by one every aspect of carbocations. Till then, bye bye.